Good day, students. Welcome to a clip on improper integrals. We're going to be dealing with type 1 today, which is the infinite limits of integration. Okay? All right, so before we take a look at the formulas and consequently an example, let's take a look at the scenario. Okay, let's say we have a function. Let's say this function is given by the equation y equals e to the negative x, and you have to find the area. Find the area under the curve. Under the curve from -1 to infinity. Okay? So that's what we have to find. This is a weird question because we have a finite number we're starting from and we're going all the way to infinity. So what on earth is this? Well, around the curve from -1 to infinity we know is simply given by the integral notation, the infinite sum from -1 to infinity of the function e to the negative x dx. Okay, so what on earth is this? Well, let's take a look at this graph. We're starting from -1, right? So this is my lower limit of integration. Draw a straight line up here. And we're going all the way to infinity. Okay, so we're looking for the area under the curve here. So is it possible for us to calculate the area under the curve from a finite number to an infinite number? Okay, like the title suggests, we're dealing with infinite limits of integration. Notice the upper limit of integration is at infinity. So is this possible? Well, let's take a look at what happens to the area as we approach infinity. Okay, we have a large area here, and what starts happening as x starts getting larger and larger, you notice that the additional units of area keeps shrinking, right? So if you think about series, when additional units of a series keeps getting smaller and smaller, what happens at infinity? It gets to a point where the additional units of area get so small that it has no additional increment, an incremental value to the area. So you see how it gets smaller and smaller? So at infinity, these additional units of area get so small that it makes no difference to the area. So what this basically means is that this area right here is convergent. Okay? It's convergent to a fixed number. So how do we find what that number that this area converges to? We just simply take the limit of this area right here. Okay, so that's how the whole idea of improper integrals comes about. We set the upper limit to a variable, and we take the limit as that variable that we set the upper limit to infinity, and that tells us what the area is. All right. So what makes this area this integral improper is because one or both of the limits cannot be approached. Okay, it doesn't have a fixed number. So this right here is infinity, is a number that you can never get to, basically. So that's why it's improper. So if the upper and the lower, not the upper, the lower, or both limits are infinity, then you have an improper integral because you can never actually get there. You can only take the limits. You can only approach them, but you can never get to them. All right. So with that idea in mind, let's write down some formulas for the three cases of improper integrals with infinite limits, and then we will apply it to an example. All right. So the title is improper integrals, type 1, which is infinite limits of integration. Okay. Now, one thing I want to note is that it's not always convergent, right? The situation can be divergent, and in that case, you do not have a fixed area. The area keeps increasing till infinity. So that's just something to keep in mind. All right, so let's write down the cases. So number one, if f of x is continuous on an interval a to infinity. So in this case, the lower limit or the left bound is finite, but the upper bound is infinite. Then the integral, the improper integral from starting from a all the way to an infinite limit, infinity of f of x dx is equal to the limit as t approaches infinity of the integral from a to t of f of x dx. Okay, so let's take a look at this notation real quick. What is this? What's happening here? You notice we said the upper limit, which is the improper limit, to t, and then we took the limit as t approaches infinity. If this limit, if the limit of this integral was a fixed number, then it's convergent, and that will be the area. But if it's infinity, then it's divergent, and hence there's no area. Okay, so this applies to scenarios where the upper limit is infinity. Now, how about if we have the lower limit as infinity? Well, let's look at case 2. If f of x is continuous on negative infinity to b, then the improper integral from negative infinity to b of f of x dx is basically equal to the limit as t approaches negative infinity uh, of the integral from t to b of f of x dx. Okay? So in this case, we're having t heading in the other direction. All right? Let me just give you a visual as to what that looks like. So in this scenario, we can do a sideways reflection of what we had initially. So we have a situation like this, like your typical exponential function, right? Let's say we're going from 1 to infinity. Notice if you're heading to negative infinity, you notice how the area starts to shrink, right? So this is a situation where you're going to negative infinity. This is a convergent scenario. It doesn't always have to be convergent. Uh, it could be divergent also. Okay, so this is just an example of a situation where the lower limit of integration is undefined, but you have a convergent area. Okay. So this is basically y equals e to the x. And the other one we did was y equals e to the negative x. Now, remember, an integral is improper if it could be the upper limit, the lower limit, or both of them could be values that you cannot reach, but you can only approach. So that brings about case number 3, where both limits are infinite. Okay? So in that case, if f of x is continuous, it has to be continuous uh, on the open interval, negative infinity to infinity, so no breaks or else we can't calculate the area, then the integral from negative infinity to infinity of f of x dx is going to be given by uh, the integral from negative infinity to c of f of x dx plus the integral from c to infinity of f of x dx. Okay? For some c and a set of real numbers. Okay? So this is basically splitting this. Whenever you have a upper and lower limit at infinity, you're going to break it up into a combination of case 1 and case 2. Okay? So that's basically what we have here. And then when we have these two, we treat them independently as though we're doing the upper problem and the lower problem. Okay? So just FYI, we have already written it, but if I wanted to evaluate this, I'll just take the limit as t approaches negative infinity of the integral from t to c of f of x dx. This is case number 2. I just rewrote here because the lower limit is at negative infinity plus, and then we have to use a limit here because the upper limit is at infinity, so we can only approach it. We can't get there. So limit as t approaches infinity of the integral from c to t of f of x dx. Okay? So if both limits of integration are at infinity and negative infinity, then you have to do more work. All right? So there you have it. All right, so in this series, I'm going to go over an easy example, and then in subsequent clips, I'm going to go do more complicated ones, okay? So example number 1, um, evaluate the given integral. And state if it converges. Okay. All right, so what we're evaluating here is the integral from -1 to infinity of e to the negative x dx. Does this look familiar? Yeah, this is the original scenario I presented to you. Okay, so just remember when you do an improper integral, is basically limits plus integration. Okay, that's all you have to do. So in order to do this, you have to know how to evaluate your limits, and you also have to know your integration techniques. All right, combination of both of them. So you do integration first, and then you apply your limit rules to whatever integral you find. Okay. All right. So what we're going to do first is let's focus on applying the formula for finding improper integrals. Remember, this is improper again because one of the limits you can only approach, you cannot get there. All right, which is infinity. So we're going to be using case number 1. So this can be written as the limit as t approaches infinity, because that's what the problem is, of the integral from -1 to t of e to the negative x dx. Okay? All right, so we see that we want to do integration first, and then we're going to do limits of our antiderivative. All right? So how do we integrate this business right here? We're going to use u substitution, okay? In this case, we're going to let u be negative x, and then du is going to be negative dx. Okay? So that this basically implies that negative du equals dx. Okay? All right. So let's go ahead and make the u substitution here. So this is going to become the limit as t approaches infinity of the integral from -1 to t. I'm not going to change the limits using my u because I'm going to switch it back after integrating, okay? E to the u, if I make a substitution here, this dx changes into negative du, okay? So I'm going to put a negative here, negative du. All right, so what is the antiderivative of e to the u? Remember, it's its own integral, right? So this simply becomes the limit as t approaches infinity of negative e to the u from -1 to t. Okay? Since I didn't change my limits of integration, I need to change this back into its original form, which is negative x. Okay, so this is still x and this is x, so I gotta change this back. So this becomes the limit as t approaches infinity of negative e to negative x evaluated from -1 to t. Okay, so I'm going to be taking the limit of this value right here. All right, so applying FTC2, we're going to plug in the upper and lower limits of integration and compute the difference. Okay, so we have the limit as t approaches infinity of negative e to the negative t, plugging in the upper limit, minus negative e to the negative 1. All right, plugging in the lower limit of integration. All right, so let's simplify this a little bit more. So we're going to have the limit as t approaches infinity of negative e to the negative t, and then this minus times minus is a plus e to the, and then this minus times minus is plus e to the 1, which is just e. All right, so there you have it. Now we're done with the integration. Now we're going to do limits. All right, so this is really easy limits to compute. But before I do the limits, let me write it in a way that's easy to compute. Okay, so I'm going to have, this is going to become limit as t approaches infinity of -1 over, using the reciprocal property of exponents, e to the t plus e. Okay, now let's take the limits, individual limits of these two. When I take the limit of this becomes -1 over e to the infinity plus this e right here is independent of this limit. So that's whatever t does, this stays is e because it is a constant. Okay? All right, so what is e to the infinity? Remember what e is like a number, right? So if you raise a number, positive number to infinity, you're going to get infinity, right? So this is going to be -1 over infinity plus e. So what is 1 over infinity? Negative 1 over infinity is going to be negative 0 plus e, which is basically e, okay, because 0 has no orientation. So guess what? That is the value of the area from negative 1 all the way to infinity. So this improper integral from negative 1 to infinity of e to the negative x dx equals e. Pretty cool, huh? All right. So thanks so much for taking the time to watch this video. Please feel free to subscribe to my channel by clicking up here. You can also support the production of this video and other videos by commenting or liking this video if you liked it. More videos can be found on math.chef.com. Thanks again and have a wonderful day.